Hi and welcome. This is the critical design review for our solar-powered UV water purifying and monitoring system. The group consists of Kendra, who is an optical engineer, Bradley, who is an electrical engineer, Lucas, who is a computer scientist, and Grant, who is another electrical engineer. We are seniors at the University of Central Florida. The sponsors for this project are Ocean Insight and BCI Technologies. Ocean Insight is a local water quality monitoring company, and they are lending us their Raman spectrometer for our water analysis. BCI Technologies is supplying some electrical equipment for implementation and testing. Some motivations behind this project are widespread viruses. As we all know, COVID-19 has been going around, and although it is not a water-based virus, it is still a good motivator for this project. UV filtration often kills viruses, and if not, it takes away their ability to reproduce. Another motivation is filtration quality. A lot of residential and portable filtration systems only come with one filter. Ours will have 2 filters and UV filtration as well. Lastly, this project was sponsored, so a lot of the financial burden was taken away, and the expensive equipment was loaned to us for us to do our testing. The main goals and objectives for this project is to create clean drinking water, offer inline contaminant and temperature monitoring, make the system solar powered, portable, and offer an interactive user interface display that will show the data being collected. The specifications for each part of the project are as follows. For the solar power system, it should offer complete off-grid operation with at least 8 hours of autonomy. For the water filtration system, it will be running at about 3 gallons per minute, have a 5-micron sediment filter, a carbon filter, and a Class C UV lamp. For water analysis, this will be done through an infrared temperature sensor as well as a Raman spectrometer. For water quality, it should be free of benzene, arsenic, and cyanide, which we will be testing for. The user interface will be a touchscreen. It will offer some control over the system, and it should be able to display certain data being collected by the system. The main specifications that we will be trying to demonstrate is successfully analyzing the water via spectroscopy, make the system fully off-grid with solar and battery dependence, and creating a user interface that will not only control the system, but it will also have data interpretation and depiction of what the spectrometer is seeing. Here is a workload distribution chart. Brad will be in charge of the solar power system, the charge controller, and the battery, that system design. Grant will be in charge of the power regulation or voltage regulation, the pump, and the initial filtration system design. Kendra will be in charge of the spectrometer, the infrared temperature sensor, and the UV water filtration system design. And Lucas will be in charge of the microcontroller and user interface design. The final design that we have come up with is this. It is a dolly system. So on top we will have our hardware and electrical panel, which will offer our PCB and microcontroller data collection. Just under it we'll have the water filtration and analysis panel. This will have the water pump, the filtration system, the spectrometer, and the temperature sensor. Below on the bottom will be the battery, and then on the back side we will have the solar panels in storage, and in theory you would roll it around, and wherever you want to place it, you will pull the solar panels out and face them toward the sun. Now you may be wondering how the whole system will work together, and to start with, the solar panels will be converting the solar energy into electrical energy. The charge controller will be in charge of charging the battery, and the battery will supply voltage to the filtration system, the spectrometer and temperature sensor, the Raspberry Pi, which is our microcontroller, and the LCD display. The unclean water is going to enter the filtration system, get cleaned. It'll be analyzed by the spectrometer and the temperature sensor. This information will be passed over to the microcontroller, and it will be then interpreted in a way that the LCD screen can display it. The solar power system will include two 100-watt polycrystalline solar panels, one pulse width modulating charge controller, and one 75 amp hour battery. The solar panels will have an RMS voltage of 12 volts DC. The charge controller has two USB ports that can power the LCD screen or the microcontroller if we need it to, and also offers protection features such as overcurrent protection, short circuit protection, and low and high battery voltage protection. It also has a user interface where we can change the battery type or charging type. The 75 amp hour battery is a sealed lead acid battery, which goes perfectly with our charge controller as the manufacturer recommended it. There were some alternative solar power parts that were considered for this project. For example, for solar panels, there are monocrystalline solar panels and thin film solar panels. Both are quite expensive compared to polycrystalline solar panels, which is why they weren't used in this project. For charge controllers, there are shunt, series, and MPPT charge controllers. A shunt charge controller will short circuit the solar panel once the battery is fully charged. A series will cut off current to stop charging in the series current loop. An MPPT one, which is much more expensive, is a maximum power point tracking charge controller. This is very widely used in efficiency stuff, where efficiency is very important, and it is quite expensive compared to the PWM charge controller. For batteries, we could have gone with the lithium ion battery, which is very expensive, but it offers very good depth of discharge and lifetime, but it needs a lot of protection circuits on it. And then there's an AGM lead acid battery, which is probably the best one. It's lightweight. It has a low internal resistance, which makes it charge faster, but it's about 2 times more expensive than the battery we're using right now.
Displayed is our complete water filtration system. It consists of a UV filter, micron sediment filter, and carbon block filter. The reason we chose UV water sanitation over any other method was because it is the #1 method to eliminate pathogens present in the water. Most water you receive through the tap has been chlorinated to remove microorganisms. However, chlorination is not successful in eliminating protozoan cysts and parasites like Giardia. In 2010, Milwaukee experienced an outbreak of Giardia in which over 400 people died since chlorination was not effective in stopping the parasite. UV filters cannot work alone though. If water enters a UV filter is not filtered down to 5 microns, there is a potential for pathogens to hide behind particles in the water and avoid exposure. Thus, we have ordered a 3-part filter which includes a sediment filter to remove particles, carbon filter for taste and odor removal, and a UV filter to remove pathogens. Most UV water filters operate at a standard household voltage of 120 volts, 60 Hz AC. Converting from 12 volts DC to 120 volts AC is a much more difficult and dangerous process than a DC to DC conversion, so we looked at alternative options. Luckily, UV water filters used in RV and marine applications operate at 12 volts DC. For the water system pump, it was crucial to find a pump that ran on 12 volts DC rather than 120 volts 60 Hz AC. It also pumps at an average rate of 2.9 gallons per minute. This pairs nicely with our UV sanitizer system, which operates at 3.5 gallons per minute. Although the pump has a slightly lower flow rate, this allows for a prolonged exposure to the UV light, which can work to disable more resistant pathogens. With our envisioned UV water sanitizer drawing water up from a local source, it was crucial that we order a self-priming and dry run capacity pump. While impeller and centrifugal pumps fail in this aspect, diaphragm pumps are a success, and that is why we've chosen this pump. This slide displays the 3 different voltage regulation specs needed for our project. These values are a result of summing the maximum current draw of components at specific voltage levels and then increasing that total by 33% as an extra precaution. There are 2 types of voltage regulators, linear and switching regulators. While linear regulators have their place in circuit design, their biggest downfall is their efficiencies. This may not matter with low power applications, but if used in our design, things would get very hot. Switching regulators offer a much better efficiency of 80 to 90% at the cost of a more complex design. Luckily, there are thousands of integrated circuits available so that engineers can implement a switching regulator with just a handful of components. Thus, switching regulators were chosen for all 3 voltage regulators. Displayed is the most complex of all our power sources. Since MOSFETs can only handle a few amps of current, this design uses multiple 12-volt regulators in parallel in order to divide the current among them. This regulator feeds power to the water system pump and the UV filter. The IC used in this design is the LM34936RHFR 30-volt wide VIN synchronous 4-switch buck boost controller. Since the largest amount of energy will be passing through this circuit, efficiency was the most important spec. This design achieved a 97.9 efficiency rating. The next schematic shows the LMZ22005TZX NOPB5A simple switcher power module. It will supply power to the Raspberry Pi and all of its accessories. One of the nicest features of this design is that it requires only 6 additional components compared to the previous design's 44. Finally, we have the TPS61170QDRVRQ1 automotive 3-volt to 18-volt wide input range 1.2 amp boost converter. This supplies our temperature sensor. Since the maximum power wasted on the schematic is only 0.14 watts, we chose to optimize BOM over efficiency since the power consumed was so insignificant. Since a microcontroller could not provide enough RAM for the data processing our design requires, no microcontroller has been included in our overall PCB design thus far. Below you can see the block diagram of our PCB. It includes the voltage sources previously discussed as well as a relay and MOSFET portion that will work with the Pi's GPIO pins to control whether components are active or not.
We chose to include UV cleaning in our system because filtration doesn't always eliminate all the viruses and bacteria in water. The wavelength for UV sanitation is from about 100 nanometers to 280 nanometers and is called UVC. Both LEDs and lamps produce this wavelength and can be used for UV sanitation. We thought a UV lamp would be the most efficient for this project because we would only have to purchase one versus multiple LEDs, and making sure the LEDs covered every centimeter of the water with equal power is much more difficult than a lamp covering both equally. To ensure the UV sanitation is effective, there are time requirements the UV radiation has to hit the water. Extremely harmful bacteria, like E. coli, needs to be UV sanitized for at least 0.3 seconds. As you can see, most of the requirements are under 1 second. So to make sure we cover all the bacteria and virus time requirements, we made sure the UV sanitizes our water for at least 1 second. To prove our system is producing clean enough water to drink, we integrated inline monitoring. The 2 main properties we are monitoring is temperature and contaminants. We chose contaminants so we could see if our water was meeting FDA guidelines for consumption. We also chose temperature because certain bacteria thrive at specific temperatures, and if even one was still in the water after it went through the filtration system at its desired temperature, it could reproduce and recontaminate the water. The temperature sensor chosen is an infrared temperature sensor. We chose infrared because it's contactless and fast. This specific sensor picks up the infrared light an object is giving off and can give a digital readout. One constraint we found with the UV sensor is its field of view. Although this hasn't brought us any specific challenges yet, it needs to be taken into account when integrating the system. Another constraint is that the water temperature will be read through a glass tube. This means that the glass temperature will be the real readout of the sensor. But basic laws of thermodynamics tell us that after some time, the glass and water will be about the same temperature, and the glass reading will be good enough to tell us the temperature of the water. We are using Raman spectroscopy for contaminant evaluation for multiple reasons. It uses minimal equipment, and the equipment is generally small. Also, when using spectroscopy, you don't have to add anything or modify the water sample. We specifically chose Raman spectroscopy because the water is a weak Raman scatterer, and therefore Raman is superior to absorption or fluorescence spectroscopy. When consulting with our sponsor, Ocean Insight, they agreed Raman spectroscopy would be the best approach and were able to lend us a Raman spectrometer and laser source for that spectrometer. Chromatography and inductively coupled plasma mass spectroscopy are two other forms of water contaminant evaluation. They have a lot of equipment and normally have to be carried to a third party, which is why we didn't choose either of these techniques. The spectrometer that was loaned to us is a 785 near-infrared spectrometer. It uses a fiber as a connector, and it also uses OceanView software. The entire spectrometer is only about 3.5 by 2 by 2 inches, so it's very small. The laser source loaned to us is a 785 nanometer source at 499 milliwatts. It is also fiber connected, and it needs a polarizing fiber, and it is 3 by 1 by 2.5 inches, so it is half of the size of the spectrometer. Each contaminant in the water will produce its own spectra. We cannot evaluate 100 plus spectras, so we chose 3 main contaminants to look for. We chose zinc cyanide, arsenic, and benzene because all of these contaminants are extremely harmful when consumed. You can see that the maximum containment level below is 0.2 for cyanide and 0 for both arsenic and benzene. Another way to ensure our water's cleanliness is by taking a Raman spectra of water that has gone through a Brita filter and water that has come out of a Zephyr Hills water bottle with our spectrometer in order to compare the spectras of our output water to see if our water matches the cleanliness, is cleaner, or is dirtier than both of those spectras. A few problems we have faced so far with the spectrometer is that we weren't able to get it until about the second week of Senior Design 2, so we haven't been able to test it. We just received the laser source 2 days ago, so we haven't been able to test that either, and we are still ordering the correct fibers to attach them together. So that's the main problem we're finding. Without it being tested, we are not able to program it yet, and we're not able to see the light dispersion through the glass tube that it will be monitoring through. So we don't know where and what exact focusing lens we need.
So as for the application part of this project, the application that shows the level of water purity to the user, it has a couple of components being interfaced. The application has 2 sensors that are being interfaced and connected directly to the microcomputer, the spectrometer and the infrared laser. The spectrometer is being interfaced using USB connection, and the sensor is being interfaced by using a control signal port that sends the data to an analog port in the microcomputer. Lastly, all the components are being powered by the PCB using wires and the microcomputer itself. First, we thought about using a microcontroller instead of a microcomputer. Reason being the microcontroller is cheaper and we'd be able to solder the microcontroller directly into the PCB, but this proved not to be possible because no microcontroller would have enough memory nor CPU power to run the application we wanted to run. So the first microcomputer we thought of using was Rock 64, reason being it was the cheapest one that passed the specs we required and had enough ports, but we decided not to use it because it didn't have the firmware to support touchscreen applications, touchscreen screens. So we decided to use a Raspberry Pi Model 4B because it had enough memory to run the application and it passed all the specs, and you also knew it would be easy to interface with the display, so we could dedicate more of our time designing the application. And here it is, the schematic of the Raspberry Pi. We decided to use a touchscreen display so the user does not need to use a mechanical pad to interact with the application. It also makes the application look a little bit fancier. So it made a lot of sense to use this display right here because this display is designed to work with the Raspberry Pi and it made it super easy to interface them together. So this way I could focus more on my time coding the application and making it look better and more efficient. And this display was also the right size you were wanting for our system. It is a standard 800 and 600 resolution and it's 7 inches across. So Ocean Insights, the company that we borrowed the spectrometer, they have their own application that's called Ocean View. And Ocean View has a more general purpose use, but our application is based on theirs. For example, in Ocean View, you can set up filters and you can look for different type of wavelengths in the spectra. But in our application, it does everything on the back end. It is looking for specific pathogens with that are represented by a certain type of spectra. Both OceanView and our application are developed using OmniDriver. OmniDriver is a library developed by Ocean Insights to control the spectrometer. They have another library called Span, but it would be not intelligent for us to use Span to develop this application, because it requires to develop our own regression algorithms, making it basically impossible to code the entire application. So the only library we're gonna use for this project will be the OmniDriver library. We'll be using the library to set an integration time for the spectra, filter noise from the data, and set triggers for the patterns we're looking for in the dataset. OmniDriver and OceanView were coded in Java, so I decided myself to code the entire application natively, and also use Java as the overall programming language for this project. I'm also familiar with Java development myself. In the documentation of OmniDriver, it's suggested to use Java to load the data using a .jar file. This application also doesn't require a big performance, since the filtering time will be much bigger than the processing time. So in order to make the application more modern looking, I decided to use JavaFX as the main framework to develop the UI of the application. So as for the operating system we're gonna put in the Raspberry Pi, well, Linux is the obvious option because there's no reason for this project to get a Windows or Mac and buy a license, so we can just get the OS for free using Linux. There are many distributions available, and I'm well versed in the dealing with Linux environment, so this is definitely an option, the best option. And Linux also has no patent, meaning we can use the software in any way and we can modify it later if necessary, but we're probably not going to modify, it's just going to be using simple setup.
When beginning this project, we set our original budget for the entire group at about $1,000 because we knew we were able to get some of the multi-$1,000 equipment loaned to us. Throughout this project, we were able to be sponsored on certain things that have helped, but we have gone a little bit over our budget and still have a few parts to order. The last few parts we have to take into account are the PCB, the overall enclosures, and some miscellaneous hardware, and the fiber and connectors for the spectrometer. This should all cost around $100, therefore we shouldn't be going over our original budget much more than $200.